Okay, so I'm sure some of you are excited to see no exams returned today. Some of you are probably disappointed to see no exams returned. Because of my travel this week, I was unable to get them graded. I will try and get them back to you as soon as possible. Historically, people have done a lot better on exam 2 than exam 1, but I don't know if that history has been preserved in this particular class. But the good news is recall that on the final, there will be the 4 sections. Section 1 will only have a relatively small subset of relatively straightforward questions. So if you can demonstrate the proficiency, right, on material balances, on phase transitions, and on energy balances, your score can rebound quite quickly, right? So don't lose hope. How many of you watched the video I posted? Okay, good. So I was planning on just maybe going over that really quickly, and I think it might be good to have a little bit of another recap on simplifying the general energy balance equations. So I'm going to go over that flash example, but I'm not going to do it as in rigorous of detail, right? Yes?
Sorry, before you start, have you also finished the regrade request?
I have not finished the regrade request. That is on the to-do list as well.
Okay, thank you.
So hopefully I can get those back at the same time for exam 2. Okay, so to round out the class, I just calculated we got about 4 weeks of class left.
What?
I know. Is that a lot or a little?
That's a little. I feel like we just started.
I don't think spring break is perfectly in the middle in the spring semester. I think fall break is perfectly in the middle of fall, but yes.
Sorry, do we have 3 midterms in this class or just the 2?
3 midterms and then the final.
So we have 1 more midterm.
Yes. On energy balances. Question? No. I think it's like a week before the end of class or something like that. So we have a couple of weeks. I'm not sure the exact date. It's in the syllabus. I'd have to go back and check. But I want to say it's like mid-ish April. Okay. So to round out what we're going to be doing for the rest of class, we've already done material balances. So that's going to be necessary to do everything. It's going to be the first step. Phase transition information is a tool that helps you do the material balances, right? When we first started in the class, it was this is the inlet composition, this is the outlet compositions, balance the total flow rates, right? Now we've taken away that information and we've said here's the temperature and pressure of the process. You determine the outlet compositions, right? So the thermodynamics are really a way for you to help to do the material balances and also help to understand the energy balances. So far, we've talked about energy balances using steam tables, where you can just look up the enthalpy, and that's where we simplify the generalized energy balance. We've started talking about on Monday, and then reviewed on Wednesday virtually, how do we estimate the phase change energies. So we've got 2 major topics left in energy balances. That's going to be talking about when you have non-ideal liquid mixtures. We're not going to talk about how you calculate that, but how you look up those values. Okay? And then a big final major topic is going to be energy balances of reacting systems, which is going to be one of the single most important concepts for chemical engineers, because we have to use a lot of energy. There's only one good, reliable source to produce as much energy as what chemical engineers consume, and that is the combustion of fossil fuels, right? So there's going to be a lot of combustion, there's going to be a lot of endothermic reactions, there's going to be a lot of exothermic reactions, and then we're going to tie all of this together with the project that will be out shortly. So the project is going to be writing your own code that basically solves an entire complicated chemical process in one spreadsheet or one MATLAB code.
Oh, that's easy.
Trivial, right? So what that means is you basically have to solve the whole system kind of algebraically. And once you have the entire system solved for the material balances and the energy balances, that enables us to do very powerful things. And that is optimization, right? If I change the temperature at one step of the process, how does that impact the conversion, the separation efficiency, and the amount of product that I can produce and sell? So chemical engineers have to take all of these concepts that we're taking apart right now granularly, and you have to put them all together into one big integrated process. Now, chemical engineers are getting so good at this, right? Does anyone know about Professor Powell's research? Professor Cody Powell. We have one individual who's aware, 2 individuals, 3-ish individuals. So Professor Powell does integrated systems engineering. So what his research group does is performs all of these mass and energy balance calculations for one process. Then it does it for the neighboring process. Then it does it for the next neighboring process. And they figure out, can I synchronize these complicated processes together such that if one is using energy at this time and not using energy at this time, can they sell and trade energy in the form of steam or unspent fuel to one another so that it optimizes the entire process. Similar goals are to integrate, let's say, a coal-fired power plant with wind farms and a solar array. How do you effectively use each source of energy at what point in time, right? So we're growing out, right, in terms of difficulty, but all of that starts with the concepts here in this class. So I think the project is really important because then you can say like, hey, what if my reactor catalyst has a problem and its efficiency drops by 5%? How much is that going to cost me in terms of money? Right? These are the questions that you can answer when you have the whole process system solved into one integrated code. Yes?
Would you allow Python code for that?
Oh, absolutely. Yeah. And this is the part where everyone gets really depressed. In the future, you won't be doing this. You'll be using Aspen, which does it all for you.
Using what?
Aspen or Promax. These are process flow simulator tools. So basically you say, oh, distillation column, click, stream in, stream out, solve it using the Penn-Robinson equation of state. But now I make you do it all manually. So you'll hate me later. Yes?
Is this group or solo project?
Solo project.
Oh, thank God.
But I'm happy if you guys want to work in groups. I think that's an excellent way to learn, right? Just make sure that the work you perform is individual. Any more questions about that? Then I'll go over. Yes? I'm hoping early next week. Yeah.
These things, the Aspen and the other thing you're saying, are those like free software or do they?
No. Very expensive software.
How expensive is very expensive?
Oh, for a chemical company to buy it? Probably on the order of hundreds of thousands.
Holy shit.
But what they do is that they say, hey, you know what, universities? You guys don't have a lot of money. We'll cut you a deal. We'll give you this for really cheap, $50 a student, right? And then you get hooked. And then you get hooked. And then you go to your company and say, I need Promax. I really need Promax. And your company goes, fine, here's $20,000, right? So that's what they do. That's why MATLAB is free almost for all the students, is they try and reel you in so that when you start your job, your company has to pay for that now. Okay. So then at the last about week or so of class, we're going to talk about transient systems. Have you guys reached initial value problem ODEs in your numerical methods class?
Oh, we're getting there.
Just getting there. Okay, good. Because we're going to be turning everything that we're doing, right? So to convert it from process engineering terminology to numerical methods terminology, right now we are solving the steady state solution to a system of differential equations, right? So if you set all those differential equations equal to 0, dx dt equals 0, dy dt equals 0, dz dt equals 0, right? That's saying that the total rate of change of mass of x, y, and z is 0, then everything on the right-hand side of the equation is now just a linear system of equations or a system of nonlinear equations, right? But if you were to simulate this as a startup and you were accumulating mass or you were depleting mass, now it's a system of ordinary differential equations. So we're going to translate everything that we've done into differential equations and then talk about how we can solve those differential equations. So having the numerical methods will be very helpful to smooth that process out. And then if time goes well, I will derive the fundamental partial differential equations that you will use in your mass transfer class and your heat transfer class. Because again, it's the same stuff we're doing right now. Okay? So For those of you in partial differential equations, we'll derive a few of those. Okay, so what we were talking about in the video lecture where I seemingly have very long hair was an acetone and benzene. Oops, that's not how you draw B. Flash separator. So we said it's 50-50 coming in at 0 degrees C and 1 mole per second total. Why do we always choose 1 mole per second for our basis?
It's easy to work with.
It's just easy to work with. Now, what if I have 1,000 moles per second? What do?
It's still easy to work with.
Just times everything by 1,000. What if I have 523 moles per second? Just times everything by 523, right? So rescaling the basis, that's why we're starting simple like this. Trivial to rescale everything at the end. The flash separator is operated at 1 atmosphere pressure and 69 degrees Celsius. So we have a vapor stream and we have a liquid stream. Okay, so if I wanted to alter the temperature of this flash separator, how would I know what are the smart and dumb ranges to operate it at? What if I operated this thing at 200 degrees Celsius in 1 atmosphere? What would I accomplish?
Nothing.
Everything would get vaporized. I would have a 50-50 mixture come in and a 50-50 mixture come out the vapor stream. Okay? What if I operated this at negative 10 degrees Celsius? What would happen? I would get a liquid stream coming in, a slightly colder liquid stream coming out with exactly the same composition. So the goal of all these separations is to slightly alter the composition of one of the streams. Once we can do that, we can keep on doing it sequentially until we purify these products to whatever desired ratio we want. So how do I know what the minimum and maximum temperature range should be? Miles?
You take the, well, I might be wrong. You take the set. Never mind. I don't know.
Okay. Ethan?
The bubble point and the dew point.
Bingo. The bubble and the dew point. So in this case, P equals 1 atmosphere. For the bubble point conditions, this is the total mole fraction multiplied by the individual vapor pressures. In this particular system, this would be a non-linear problem that we would have to solve. Okay? So I would have 0.5 and 0.5, and then I wouldn't know what temperature it was, so I couldn't look up the vapor pressure, but I could substitute in Anton's equation parameters, and it would be a complicated looking equation, but it would still just be one equation and one unknown, right? So here I can solve for, in this case here, this is the bubble temperature, so T bubble would be equal to 65.7 degrees C. So if you want, you can go back and double check my work, look up the Anton parameters, solve for the bubble temperature there. Alternatively, we can also still set the temp pressure to equal to 1, but in this case, we'll use the equation that we derived for the dew pressure. Even a less pleasant looking nonlinear equation, but do we care, right? Does MATLAB or Excel really care that much to solve this equation nonlinearly or this equation nonlinearly? This is child's play for how powerful our computers are, right? So doesn't really matter how much algebra you want to do on the page, just dump it in the computer, it'll give you the right answer. Now, in your numerical methods course, if this function is not well behaved and you find yourself at a 0 here in the denominator, well, then yes, you could have some problems. But give it a good enough initial guess and you'll avoid that problem. And the dew temperature is 70.2 degrees C, okay? This is just a recap, just to make sure everyone's on the same page, how everything ties together. Now that I know the range, if this was my process that I was trying to optimize, there would be some rational basis for what temperature I wanted to operate this thing. The closer I get to the dew or the bubble point, it sort of gives me the extrema of the most separation versus the least separation, right? So as a general idea for these Raoult's law systems, the more pure you make your vapor stream of your volatile component, the less of that vapor stream you will get. Right? So the maximum amount of acetone that I get in the vapor stream corresponds to the minimum amount of vapor that you would produce, which is the bubble point condition. Right? So there's not a clear-cut answer of at what temperature should you operate this process at. It has to be integrated into an overall system, so then you can make that judgment. Okay, so what's the next step if I want to understand this process? I know the temperature, 69. What do I need to look up? We need now our saturation pressures. So the saturation pressure for acetone at this temperature is 154.4 kilopascals. The saturation pressure for benzene is 71.0 kilopascals. Okay? Now, do I have all the information I need to complete my material balances? Yes, I do. I just need to solve the flash problem. Okay? So just solve the flash problem. And there you go, solved. Okay? So what I'm going to do is I'm going to put this into a big table. Okay? So we have our feed, our flow rates of the feed, and I'm going to bake in the enthalpies of my feed, because I know I'm going to have to do the energy balance for this problem as well. The liquid stream, the enthalpies of that stream, the vapor, the flow rates of that stream, and the enthalpies of that stream. Okay, so now if I'm going to throw in my balance, let's say we magically did it. So this is for acetone, this is for benzene. We start off with 0.5, 0.5. Once we do the flash calculation, we can see that in the liquid, it's 0.100, 0.176, 0.399, 0.322. And hopefully everything adds up to 1. So all of these should add up to 1, because this is the total out and this is the total in. It seems about right. Okay. So now we have to fill in our enthalpies. Get out of the way. Question?
Is there actually a process that exists and that they do in industry where they have an acetone and benzene?
Probably not, no.
Okay.
I don't think so. This is an arbitrary selection. But if you notice on the exams, I do try and write real processes on the exams.
Ni and Ni for liquid vaporage are calculated, right? You just have them.
These are the flash calculations that I skipped over based on this vapor pressure, those inlet flow rates, that temperature and pressure. Unless I screwed up, this is what you should get for your flash. Okay. So in the example that I gave on Wednesday that I'm redoing now, I selected a reference state of the liquid as having 0 enthalpy. So what I'm saying is that at 69 degrees Celsius and 1 atmosphere at a liquid, therefore the enthalpy equals 0. That's what I'm stating here. Now we just did a problem on the quiz. What was the reference state for that? Not quite. So that was the pressure of 10 bar. But those numbers, none of those numbers were 0, right? So why do I have a 0 here? What's the 0 on those steam tables?
It was some value below saturated liquid, probably like
I think yes, exactly. So the common reference state is the internal energy of saturated liquid water at 0.01 degrees Celsius is enthalpy equals 0. Okay? I could do exactly the same thing here. I could say that at 0 degrees Celsius for a liquid, for benzene and for acetone, my enthalpy is equal to 0. Nothing stops me from doing that. I would get exactly the same answer here, assuming I had perfect data for thermodynamics. Okay? What's nice about choosing a reference near to the physical process is if you don't have perfect data, those inaccuracies start to add up and accumulate. Right? So if I don't have access to perfect heat capacity, if I have access to perfect heat capacity, right, this is an exact mathematical relationship here. If I have perfect heat capacity, it doesn't matter what my reference state is. But if I have some inaccuracies in my heat capacity, right, they may accumulate. Or it's nice to just set some of your terms equal to 0. So that's another asset of choosing this. Okay? What I want you to all understand is that just because I chose this reference state, that doesn't mean you cannot do the problem in a completely different way. You could solve this with the vapor as your reference state. You could solve this with your feed as your reference state. The most important thing that you need to understand about these thermodynamic problems is how do I get from my reference state to my final state? What are the steps I'm going to take? Where do I get the data from those steps? So let's write out the energy balance, du dt, change in total internal energy of the system per unit of time. If this is an open and steady state process, we set this equal to 0. That is the summation of the flow rates and the enthalpies into the system minus the flow rates and the enthalpies out of the system, plus any heat that comes in, plus any work, plus, minus any P dV dt. So that's going to go away, that's going to go away. And we get that Q is equal to the summation of flow rates, enthalpies out, minus the summation of flow rates, enthalpies in. The energy balance contribution here is very, very trivial. Right? Once you feel confident simplifying the generalized balance, I have this equation. I can calculate this very easily in Excel. On your calculator, a little bit less pleasant, right? Because I have let's see how many things. Coming into the system, I have 2 flow rates and 2 enthalpies. Leaving the system, I have 4 flow rates and 4 enthalpies. So that means this summation here has 6 different terms. 2 flowing in, 4 flowing out. So that's just a lot of typing you got to do in your calculator. So easy to make a mistake there. So now the challenge of these problems is not composing the energy balance, because this energy balance right here is going to look very, very similar for about 90% of the problems that we're going to be doing in the class. Okay? So for reacting systems, same energy balance. Right? Hard part is coming up with these enthalpy values. The reason why I like this approach for the reference state is because it makes it relatively straightforward. So going from the liquid, which is enthalpy 0, to the feed, is the feed liquid or vapor? Liquid. Right? You could confirm by looking at what the vapor pressure is at 0 degrees C, and you will find that the bubble point is significantly below 1 atmosphere. Right? So it's going to stay liquid. So do I have to do a phase transition going from the liquid to the feed? So all I have to do is heat or cool each of these liquids individually. Yes?
So if we were operating at something other than P atmospheric and it said that the feed was coming in at a different pressure, then would we have some work term as well in
You could have a delta PV term as well.
Okay.
But in general, we'll probably just neglect it. Unless it's like 1,000 atmospheres, we can neglect that. Yeah. For liquids. For vapors, no. It's a big deal for vapors. Okay, so the enthalpy, all of our enthalpies should start off with a delta H. And then we want to work backwards from there. Okay? So we only know in thermodynamics how to calculate changes in enthalpy. This is because we don't know how to go all the way to absolute zero. And we don't need to know all the energy. So all of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, it's always du, ds. It's not u equals, it's not s equals. It's the rate of change of energy, it's the rate of change of entropy. So we should always be starting off with a delta H, choosing how we want to accomplish that, and then substituting and solving. So for delta H, going from the liquid to the feed, okay, this is going to be final minus initial. So we're looking at a temperature change of a liquid. So this is then going to take us from the temperature of the liquid to the temperature of the feed, the heat capacity of whatever species we're looking at in the liquid state, dt. Delta H is also equal to final minus initial. So that tells us that this is equal to the enthalpy of the final state, or the feed state, minus the enthalpy of the initial state, which is the liquid state. Now look at this. By choosing my reference cleverly, this term goes to 0. So now the number that I want to put in my table is just this integral. Look up the heat capacity, integrate it from the liquid temperature of 69 to the feed temperature of 0. Now, this is higher than this. So what does that tell us about the integral here? It's negative. Is that a problem? Did we make a mistake? No. Doesn't matter. Doesn't matter, right? So if we apply that, we're going to get that this value here is minus 8.9. And these are in kilojoules per mole. And minus 9.3. Yes?
So the reference state calculation works because the difference between them will always be the same?
Correct. So if I chose a reference state of, let's say, well, we could flip it and say, let's say the reference state is 0. Okay? That means that I would then go from the feed to the liquid state, and that would be from 0 to 69, and that would mean exactly the same temperature, enthalpies, but just it would be a positive as opposed to a negative. Now imagine I chose negative 20 as my reference state. Well, then the energy that it would take to go from negative 20 to 0 would be the same for this one, and it would be the same for this one. So it would just cancel out when I took the difference between the two of them. And that's exactly what you're doing when you use the example in the quiz for the steam tables, right? That energy that it took to go from 0 to whatever values we were talking about is the same for all of those different streams. It all cancels out. Okay? So far, so good, right? Now the harder one, well, it can be harder, it can be easier, is now we're going to go from the from the liquid stream to the vapor stream. Okay, so we have to then construct a delta H. So delta H going from the liquid stream to the vapor stream is going to be equal to the enthalpy of the vapor minus the enthalpy of the liquid, right? Oh, well, it's really convenient. That's equal to 0. So now whatever delta H I calculate is the number that I will put into this table here. And on Monday, we talked about a couple of strategies of how to do that. Okay? So this is exactly equal to the heat of vaporization at temperature equals to 69 degrees Celsius. Okay? So now the question is, how do we get the heat of vaporization at 69 degrees Celsius, right? I'm not changing the pressure, I'm not changing the temperature. That is just the heat of vaporization at that state. Well, in the back of the book, we would have the heat of vaporization for benzene at its normal boiling point. So T of acetone is, for its boiling point at 1 atmosphere, is 56 degrees Celsius. And the benzene boiling point is equal to 80.1 degrees Celsius. These have heats of vaporization of 30.2 kilojoules per mole and 30.8 kilojoules per mole. Okay? So we can use the Watson correlation, right? That's one of the correlations we talked about on Monday. That's probably the best, most reliable one to use, particularly because it just perturbs in the neighborhood of where the normal boiling points are, right? So we could just use the Watson correlation and directly calculate the heat of vaporization for acetone and the heat of vaporization for benzene. Does that make sense? So you'll have to do this on your homework, so it'll make more sense then. The other option is that I can choose a different pathway. Okay? So let's talk about the delta H for acetone going from the liquid to the vapor state. So if I only have access to the enthalpy of vaporization at the normal boiling point for acetone, I can just march my way down a path to get there. So the liquid here is at 69 degrees C. I want to get to 56 degrees C, which is the normal boiling point, heating up the liquid, right? So now I've taken my liquid and I've cooled it down to its normal boiling point. Then I can vaporize it, delta H acetone vaporization at T equals 56 degrees C, which is that one right there. Now I have a vapor at 56 degrees. So then I need to get it back to the state that it wants to be at, which is going to be heating from 56 to 69. But now this is the heat capacity of the vapor. If the heat capacity of the vapor is the same as the heat capacity of the liquid, then these two terms cancel out and the heat of vaporization is not a function of temperature. But the heat of vaporization is a function of temperature, which means that the vapor and liquid have to have different heat capacities. Okay? Now, lastly, we can do the same thing for benzene, delta H for benzene going from the liquid to the vapor state. In this case, we are going to go from 69, which is our starting temperature, to 80.1, but the heat capacity of benzene liquid. Then we are going to vaporize benzene, but this case at 80.1 degrees Celsius. And then we are going to cool down its vapor from 80.1 to the 69 C sub P of the vapor of benzene vapor dt. Okay? If we have access to the data, we can do this. Now we can simplify this. What if we have a constant heat capacity? Well, then that just simplifies how you do these integrals. What if we don't want to bother with any of this and a back of the envelope calculation is fine? You can use the Watson correlation, right? You can estimate the heat of vaporization using other means and correlations that we talked about. But the key thing is knowing what your path is going to be dictated by what data you have available. Okay? So if I plug these numbers in, right, recall that this delta H path that I took going from the liquid to the vapor state takes us from the vapor to the reference. The reference we said is equal to 0. So now we only have a simple calculation to fill in our tables. So these numbers here are 29.5 and 31.3. Now that we have all of our flow rates, all of our enthalpies, it's a plug and chug problem for our energy balance. And we get that Q is equal to, where's my final answer? 30.9 kilojoules per second. Okay? That is the example problem we did. Should have done on Wednesday. Yeah, Miles.
So the numbers on the control cycles for reading 69 and 80.1, the other one goes from 69 to 56. How does
This is, so very good question. Right, so when we're choosing this, right, we have to move in a straight line fashion. So we go from 69 to 56 because we have data of vaporizing at 56, and then we have to go back from 56 to the process temperatures. Now in the case of benzene, we're going from 69 to where we have the data for the heat of vaporization. Let's say you had data for the heat of vaporization of benzene at 22, then you could go down to 22 if you wanted to. Okay.
So our options are to either do that halfway or use the equations we learned Monday.
The correlations, yeah. But it's dependent upon what data you have access to. So in the real world, you may not have access to even heat capacity data of a new product.
Right. So
Yeah.
you need to adjust